Hello everyone. So today we are going to talk about asymptotic analysis. The first thing we are going to discuss is probability. Okay. So a random variable is a function that maps a measurable space to the real line, what is R1. So what is a real line? So it's from minus infinity to positive infinity, right? And it does not include infinity, right? So it's actually the parenthesis here. Um, and the a random variable x is defined on the measurable space, so it maps the elements in the measurable space to the real line. So you can imagine, suppose we have something this is the measurable space, and there's element here, there's element here, omega 1, omega 2, and x is mapping these things to a real line R1. Right. This is x, a random variable. Okay, and subsets of omega are co-events that can be assigned a probability measure. Right. So for example, if we collect all the events like a small omega such that x omega less or equal to a, let's say these are 1, we collect this and maybe this, and let's say x omega 1 is 2, x omega 2 is 3, and x omega 3 is say 4, and we want to collect let's say we want to collect all x omega less or equal to 4, and we collect all these 3, and we give them assign a probability here. So we assign a probability of this small omega. Then that's how we define the probability, right? That's a probability of x less or equal to a, right? We calculate this intuitively. We calculate the area of this W1, W2, W3, these events in the measurable space omega. And we calculate or we collect this event and assign a probability on these events. Okay? And for probability, we can also define, for a random variable, we can also define the cumulative distribution function, the CDF, which is a function fa such that fa equals to p, the probability of the random variable x less or equal to a number a, and the function is defined on the number a here. And we know that because a is from the R1, the real line, so it's the smallest can go is minus infinity, the largest can go is infinity. Also, we know probability must be between 0 and 1, so that means the CDF, the smallest CDF should be 0, the largest CDF, the value should be 1, right? So f here, the CDF when a equals minus infinity should be 0, the CDF should be 1 when a equals infinity, or when a approach to infinity. Okay. Also, the CDF must be non-decreasing, so it can either goes up or flat. It cannot go down. That's very intuitive because we are because it is cumulative distribution function, right? So it must goes up or stay flat. Also, it is something we call right continuous. Okay, let's see. So this is a CDF for a standard normal distribution. Right. You can see when x equals 0, the CDF value equals 0.5, right? Because 0 is in the center, right? It's a standard normal, so it's actually at the center. So half of the probability should be 0.5, right? And it can goes to minus infinity, and it will approach to 0. When it goes to the other end, it will approach to 1, right? When that goes to infinity. Okay. And apparently this is increasing, right? So the CDF for the normal for standard normal random variable is increasing because it is continuous. If you take derivative of the CDF, we will have the PDF, right? The probability density function, and we all know for standard normal distribution, it has a bell shape, right? It's centered at the 0 and with a standard deviation of 1, right? So that's why half of the probability will be 0.5, right? So that's the area below the PDF, right? And of course, the whole area below the PDF will have a probability 1, right? So that will be 1 here, right? The CDF. Okay. And this is a case of a discrete random variable. And this you can see why a CDF is non-decreasing, right? So this is stay flat, then have a jump, then stay flat, then another jump. Also, you can see that this is right continuous, right? It's continuous from the right, but not from the left, right? From the left here is a jump, so it's not continuous, but it is continuous from the right. That's why we call this is right continuous. Okay, and this is a PDF with say when x equals 0, the probability will be the jump, which is 1/4. When x equals 1, the jump will be 3/4 minus 1/4 here, which will be 1/2. And when x equals 2, the probability will be 1 minus 3/4, which will be 1/4. Right, so this is a continuous random variable, and x takes only 3 values, 0, 1, 2. Okay. Right, we can also write down the CDF, right? Apparently, the CDF will be x less than 0 will be 0, right? When the random variable less than 0 is the cumulative probability is 0, and when x less than 1, the cumulative probability will be 1/4, and when x less than 2, the probability will be 3/4, and when x greater or equal to 2, the cumulative probability will be 1. Right. So, yeah. So this is an example of a CDF for a discrete random variable. Right. Some people actually say random variable is not a good name because it is neither random nor a variable. Right? It is a function. It is a function with probability attached to some values, right? So it is not random, and it is not a variable. It's a function with some probability measure. Okay. The next thing we are going to talk about is mode of convergence. So let's start with the non-stochastic case, So this is just the limit, right? So the non-stochastic convergence is what we already learned in high school, the limit, right? So there is a sequence x1, x2 to xn, and xn approach to x its limit. But how to define the limit formally? So here is the language, right? So if you take real analysis, this will be the starting point of a real analysis. How to define a limit? Okay, so this is the language. For every epsilon greater than 0, there exists an n epsilon such that the distance xn minus x less than epsilon for all n greater or equal to n epsilon. The definition, I mean, it reads very confusing, but it means that the distance between xn and x can be made arbitrarily small. Let's see. So this is x. This is x, and we have an epsilon. We have an epsilon ball. Let's say we have an epsilon ball here. Okay, and this is x1 and x2, and it will go on and on, and it will enter the epsilon ball. Okay. So let's start with, say, epsilon equals 1, and let's say when x equals 100, x100, it will enter the epsilon ball. And the non-stochastic convergence says for anything above 100, all of the xn must be fall inside the epsilon ball. So x 101, 102, and go on, all must inside this epsilon ball. Furthermore, we can make the epsilon ball arbitrarily small. So let's say we can make epsilon equals 0.5. So the epsilon is half the size. Again, there will be a number such that all the n after that number will fall inside the epsilon ball. Let's say this is actually x200. So x201, 202, and go on, all of the xn should fall inside the new epsilon ball. And because we can make this epsilon ball arbitrarily small, so that means we can make smaller and smaller, and we can force the xn closer and closer to the x. Okay, so that's the definition for limits or non-stochastic convergence. Okay, we can make the xn. We can basically we can make the distance between xn and x arbitrarily small. And we can generalize the definition of convergence to a probability space or a measurable space. Okay. Of course, it will be a bit more difficult and tricky, right? Because now xn are not just numbers. They are random variables. They are functions. So let's say x1 to xn, they are a sequence of random variable, and its limit x could be either a random variable or in a simpler case, it could be just a constant. Okay, but in general, they are all random variable, and they could be a vector. Right? In general, we are dealing with a vector of vectors of random variables. So each xn could be a vector. The first one is the first stochastic convergence we are going to talk about is called almost surely convergence. So xn converge almost surely to x if the probability that xn converge to x equals 1. So equivalently, that means the probability of that xn does not converge to x, its probability equals 0. In this case, we write xn converge almost surely to x. The almost surely convergence has similar property as non-stochastic convergence. Okay, it's actually very similar, but it allows some xn not convergent to x. Okay, but this non-converging xn must have a probability of 0. So the set of xn that does not converge to x has major 0, regardless of n. Okay, so basically we say there could be some x, let's say x 150 is not inside the epsilon ball, but these x that are not inside the epsilon ball has major 0, and also it's major 0 regardless of n. Okay, so the total number or the total probability of xn that are not inside the epsilon ball is fixed, and they have a probability of 0. So note that probability 0 does not mean the event does not exist. Okay. Remember, if you right, so think about this is just a PDF. How do we calculate? How do we get probability? Well, the probability is the area below the PDF, right? So usually we have like probability of a random variable. This is the probability, right? This is the area, but the probability of, say, a continuous random variable x equals to a point A usually is 0, right? For example, if x is a normal distribution, the normal random variable equals to, say, 1, the probability will be 0, right? Because for a single point, there's no area, so the probability will be 0. But it does not mean that this point does not exist, right? So major 0, it just means there's no probability. Sorry, it just means the probability is 0, but it does not mean they do not exist. So in other words, convergence, almost surely convergence, allows some point outside the epsilon ball, but this point needed to have a probability of 0. In other words, it's actually kind of similar to the non-stochastic convergence, which just allows some exception, a small set of exception. Okay, so the next is the most important one, convergence improbability. So xn converge in probability to x if for any epsilon greater than 0, the probability that xn minus x less than epsilon, the probability approach to 1. So the probability that xn fall inside the epsilon ball approaching to 1. Equivalently, the probability that xn outside the epsilon ball, the xn outside the epsilon ball approaching to 0. Okay, it does not say the probability is 0. It only says the probability approaching to 0 when n goes to infinity. In other words, the probability is not 0. Okay, it's only getting smaller. In this case, we write xn converge in probability to x, or more commonly, we write p-lim, probability limit. P-lim xn equals x. The probability that xn is arbitrarily close to x is approaching to 1. Here, or equivalently, the probability that xn outside the epsilon ball approach to 0. For any finite n, right, in real world, we don't have infinite number. We only have a finite number n. The set of xn that does not converge to x may have a non-zero probability. We only require that to be decreasing and approaching to 0. Right, so clearly, convergence in probability is weaker than almost surely convergence. Right, you can see this figure. Right, so here we show that xn converge in probability to a point A. Right, there's epsilon ball here. It's an interval, so right, A minus epsilon or A plus epsilon, and you can see the area outside the epsilon ball, outside the interval, is not 0, but it is decreasing and approaching to 0, right? So when n goes to infinity, the xn outside the epsilon ball should be 0 when n approach to infinity. Right? But it's very different from the almost surely convergence, which require the probability here always be 0 regardless of n. Okay? Right. In almost surely convergence, all this area must be major 0 regardless of n. Okay? There are two more convergence. One is called xn converge in min R to x. So that means the expectation of power R, basically the R's moment, its limit must be 0. And we write xn converge in min R to x. In econometrics, the most common one is when R equals 2, that's called mean square convergence. Right? So it's xn converge in mean square to x. The last one is also very important. It's called convergence in distribution. So xn converge in distribution to x if its CDF, the limit of the CDF equals to the CDF of the x for all continuous points of f and a. In this case, we write xn converge in distribution to x. Apparently, this is weaker than converge in probability, right? Because we don't need the two random variables to be arbitrarily close to each other. We only need their CDF to be very similar, nearly identical. Right? We only need the CDF for all the continuous points to be identical when n goes to infinity. This is also a very important one. So in econometrics, we mostly interest in converge in probability and converge in distribution. We are going to talk about the law of large number, which relies on convergence in probability. And also, we are going to talk about the central limit theorem, which relies on convergence in distribution. Okay. Converge in mean square also common in econometrics as well. Okay. So here are some useful results. so we already talked about this, right? Almost surely convergence is stronger than convergence in probability, so it implies, so almost surely convergence implies convergence in probability. Mean square convergence also implies convergence in probability. There is something called Chebyshev inequality. We don't have time to cover that, but you can just look at some textbook or just Google that. You will see the proof. Importantly, convergence in probability implies convergence in distribution, right? Like I say, it's actually very intuitive because convergence in distribution only requires the CDF to be almost identical. Okay. And it can also be shown by the asymptotic equivalence lemma we're going to see shortly. So a special case here, if the limit is a constant, it's not a random variable, then convergence in probability is the same as convergence in distribution. Obviously, if it's not a random variable, of course there's no CDF, or the CDF is just a point, so convergence in probability and convergence in distribution should be identical. Okay, so next, the continuous mapping theorem. This is very, very important. Okay, so let G be a continuous function with respect to x. Then we can pass convergence in probability into the function. So if xn converge in probability to x, gxn also converge in probability to gx. This is extremely convenient. And because probability convergence implies convergence in distribution, so convergence in distribution also true, right? So if xn converge in distribution to x, gxn also converge in distribution to gx. So here's an example, right? Let's say we want to estimate the mean of y. We know we can use y bar, the simple average, to estimate the population mean. And we know by law of large number, the peeling y bar equals the population mean, right? So the y bar converges in probability to the population mean. But how to estimate 1 over mu, right, the inverse? Well, by continuous mapping theorem, we know that we can just use 1 over y bar here as an estimate for 1 over mu, because the inverse is a continuous function, so the peeling 1 over y bar will equals, so peeling 1 over y bar will equals 1 over peeling y bar equals 1 over mu. And note that if expectation, with expectation you cannot do that, right? We know the expectation of the sample of y bar equals mu, but the expectation of 1 over y bar does not equal 1 over mu. So to generalize that, so we have something called Slutsky theorem, right? So there's just an application of the continuous mapping theorem, right? So let's say xn converge in distribution to x, yn converge in probability to y0, a constant. Then xn plus yn converge to x plus y0 in distribution. Similarly, xn times yn or xn divided by yn also converge in distribution to either y0 times x or x over y0. So when we combine converge in distribution and converge in probability, the convergence can pass through, but we only have the weaker form of convergence, which is convergence in distribution. Right. Also, note that the Slutsky theorem may not be true if yn also converge to a random variable. Right here, it is only true if its yn converge to a constant. Okay. Asymptotic equivalence lemma. If xn converge in probability to Zn, or equivalently, you can write xn minus Zn converge in probability to 0. In fact, that's a more formal way to write down convergence, like a sequence of random variable converge to another random variable. This way is actually a more formal way to write down the convergence. But anyway, so let's say xn converge in probability to Zn, another sequence of random variable, and Zn converges in distribution to Z, another random variable. Then we have xn converge in distribution to Z. So in other words, here is a transitivity, right? But we only have the weaker form of convergence. Okay, so xn converge in probability to Zn, Zn converge in distribution to Z, then xn also converge in distribution to Z. So there is a transitivity, but we only have the weaker form of convergence. Okay, next, if xn converge in probability to 0, then we call xn small op1. More generally, if an is a non-random positive series and xn divided by an is small op1, then xn is called small opan. For our purpose, I think we will only deal with small op1. That's the most common one we are going to use. Similarly, we can define something called bounded improbability. For every epsilon greater than 0, there exists a m which depends on epsilon, and a n also depends on epsilon, such that the probability that xn greater than m less than epsilon for all n greater or equal to n epsilon. It's just the definition again looks a bit confusing, but it simply says that the random variable xn are bounded by some m. Okay, we can always find some m that greater than xn. It's just bounded. Okay, and because it is in a probability sense, so we allow some xn greater than the bound, but that should converge to 0, right? So the probability that greater than the bound should converge to 0. And in this case, we say xn is big op1. Again, if an is a non-random positive series, xn divided by an is big op1, then we call xn big opan. Again, for our purpose, we are going to only deal with big op1. So why do we need small op1 and big op1? Well, because they are very convenient. So let's see. So first of all, if xn converge in distribution to x, then xn is big op1. This is very intuitive, right? Because if xn converge to a random variable in distribution, then of course um, the xn must be bounded by something, right? So xn must be big OP1. Also, because we know if xn converge in if xn converge in distribution to x, it implies if xn converge in probability to x, that implies xn also converge in distribution to x, right? So therefore, if xn converge in probability to x, then xn must be big OP1 as well. Also, we know xn, by definition, xn minus x must be converge in probability to 0. So xn minus x will be small OP1. In a probability sense, small OP1 can be treated as 0, and big OP1 can be treated as a constant. So for example, small OP1 plus big OP1 will be big OP1. Small OP1 times big OP1 will be small OP1. Small OP1 times small OP1 will be small OP1. Big OP1 times big OP1 will be big OP1. So later when we try to show like consistency or something else, we will use this small OP1 and big OP1, right? Because if we can show something converge in distribution or in probability to something, then we know that thing is small OP1. We know that thing is big OP1, right? And if we can also show something like it's small OP1, then this relationship here will be really useful, right? It's essentially these small OP1 and big OP1 are simply convenient notations that can help us can help the derivation of some mathematical equation, will make the derivation of some mathematical relationship become easier. Also, keep in mind that all variables in econ 4a are generally vector. They are generally random vector. They are vectors of random variables.